Welcome to the Problems Channel Season 3, Episode 26, the episode which I titled A Kinematic Descent of a Rotating Line Segment, because in this episode we will investigate precisely that, a kinematic descent of a rotating line segment, and we will analyze that motion of one of the extremities of such a line segment from a kinematic standpoint. We will discover the trajectory that is traced by that point. We will deduce its velocity and acceleration and the curvature of the resultant trajectory. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the home page of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety because we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you, and I will take it from there. And as always, and of course, I would like to extend my deepest gratitude to all the current supporters and the current subscribers of our channel. In the physics problem S3E26, we are given a line segment of length r trapped between the points A and B, and we are told that again in the kinematic fashion we are ignoring all sorts of forces. This is a mathematical thought experiment, if you will. Our line segment of length r is rotating about one of its extremities, let's say the point A, and we're interested in the behavior of the point B. Now, as the line segment rotates about its point A in the horizontal plane with the constant angular velocity omega 0 is a constant, the line segment also uniformly descends in the, let's say, uniform near-Earth gravity. That means that the, let's say, center of mass or the entire line segment, every point of this line segment, moves downward towards the Earth's surface with the constant velocity, linear velocity v0. v0 is a constant. In other words, our line segment participates in a composite motion or two independent motions that superimpose onto each other. A uniform descent in the uniform near-Earth gravity, let's say, with the velocity v0, and the uniform rotation in the horizontal plane about one of its extremities with the constant angular velocity. And the objective in this problem is the following. We need to do four things in this problem. We want to recover the velocity v of the point B as a function of time, the acceleration of the point B as a function of time, the trajectory of the point B. We want to figure out what is the spatial curve that the point B traces as it descends. And we want to find number 4, the task number 4, we want to find the curvature of this trajectory. And it should be understood that my requirement that the line segment descends is just perhaps one romantic way to look at the problem, because in a quite similar fashion, the line segment would be ascending or rising also with the same angular velocity. Fundamentally, it doesn't really matter. If I were to call this problem not too difficult, that would be an understatement. In reality, this problem is actually very, very straightforward, and it is so straightforward that it is a perfect candidate for a verbal face-to-face real-time examination as an icebreaker or as a conversation starter to see if the student is aware of what is going on in this particular discipline. And we begin solving this problem in a way in which we solve similar problems in mathematics. That is, we temporarily suspend the variance of all the other multiple quantities, and we try to wrap our brain around the behavior of just one varying quantity. In this particular case, the point B participates in a total motion that is a superposition of two independent motions, a rotation and a translation, a vertical translation. By the problem statement, we're told that the line segment descends at a uniform rate in the near Earth gravity, and this is actually quite straightforward to imagine, but it should be evident that due to the symmetry of the problem, our line segment could be ascending at a uniform rate just as well. But let's say our line segment is descending, as I declared in the title of this episode and in the problem statement. We now temporarily suspend the translational motion or the vertical translational motion of the line segment, and that means we will only consider the rotational motion. And we're told that the line segment of length r0, here I designated the length of the line segment not with the symbol r but with r0, because anything with 0 subscript designates a quantity that does not vary over time or remains constant. We're told that this line segment rotates in the horizontal plane about the point A. And now we recall the basic theorem from elementary plane Euclidean geometry, according to which any plane that is rotated about a point, about a fixed point, not about the straight line, but about the point, is a transformation that has one and only one fixed or stationary point, and that point is the center of rotation. Since in our case the point A is the center of rotation, then under the temporary suspension of the vertical translation, we now understand that the point A remains stationary, logically stationary at all times, where every other point of the line segment rotates in the horizontal plane about that point. Now we switch things around and temporarily suspend the rotational motion and only consider the vertical translational motion of the line segment. We see that the point A, logically speaking, moves strictly down if we take the descent as our mechanism, or like I said before, the point A can be climbing vertically back up. It doesn't really matter. Fundamentally, this direction of the motion of the line segment does not make any difference for the structural solution that we're about to develop. And that tells us that it is natural to put the point A, onto the z-axis, of a traditional orthogonal right-handed three-space coordinate system. Right-handed means that if we sit on the positive branch of the z-axis and look onto the x or y plane, that means that in order to make sure that the positive branch of the x-axis coincides through a rotational motion about the origin with the positive branch of the y-axis, we need to rotate that positive branch of the x-axis counterclockwise. In other words, let's say we can direct the x-axis this way and the y-axis, for example, that way. This will be our y-axis. So now the point A descends uniformly over the chosen orthogonal three-space right-handed coordinate system. Right-handed means that if we take the palm of our hand and rotate the x-axis toward the y-axis, the thumb points at the positive direction of the z axis. And we can right away, because we're told that the line segment descends at a uniform rate, or we can also conduct a thought experiment in which the line segment ascends at a uniform rate. We can write the equation of motion for the point A right away. It will be the following. The z coordinate of that point will be, in our case, we figure it will diminish over time, so we will write it with the negative sign, v0 times t. This is directly from the problem statement that we're given, and this particular expression simply means that at the initial moment of time when t is equal to 0, we chose a specific coordinate system with a specific origin. When time is 0, the z coordinate is evidently 0. So to be completely pedantic, we could put the z0 sub-0 minus this, but we will keep it that way with the understanding that the sign over here is largely cosmetic. It could be the plus sign just as well, which will correspond to the uniform ascent of the line segment in the uniform Earth gravity with the constant by direction and magnitude velocity v0. Now, once we understand that, we now switch again. We temporarily suspend the uniform translational motion of the line segment in the vertical direction. Go back to the rotation. If we suspend our translational motion of the line segment at any plane z equals to const, whatever it is, certain number z0, then we will realize that again the line segment participates only in the rotational motion, and the position of the point B in the frozen plane at any moment of time will be what? It will be described by a position on a circle of radius r0, and the center of that circle will be located precisely somewhere on the z-axis. Where? Well, exactly at the point where the z equals const plane intersects the z-axis. And if at that moment of time we orthogonally project the point B, if we orthogonally project the point B onto the point B, let's say xy in the x or y plane, then what would that mean? That would mean that our point B is located somewhere on the periphery of the unit, not unit, but origin-centered circle of radius r0. So this distance will be r0, this distance will be r0, and this will be the location of our point B. And now it is evident that the position of this point, which is the orthogonal projection of the point B, can be described which way? Let's say we erase our thought experiment here, and we can right away write down the expressions for the x of t as r0 times the cosine of something, and then y of t will be r0 times the trigonometric value of function sine of something. Now, what is that something? What is that angle right here? Let's say this will be our angle theta. It will depend on the time t. In which way? Well, we're told that the rotational motion of the point B is uniform. That means that the angle by which our point rotates with respect to, let's say, positive branch of the x-axis in this direction after time t will be given by omega 0 t. In other words, the angle depends on time linearly. In the time t is taken in the first degree. So omega 0 t, where t is the parameter, and this omega 0 t is a parameter where t varies from t varies from 0 and to some value. Now, how do we connect the point Bx with the point B? Well, we now understand that the line segment AB is a body that is absolutely rigid, which means that under any motion, rotational or translational, the distance between any two distinct points on that line segment remains the same at all times. And that means that our point A, for which we wrote the equation of motion over the axis Z, plays the role of what? It plays the role of an orthogonal projection of the point B onto the axis Z. And now we have the understanding of the fact that the behavior of the coordinate Z over time, shown over here, minus V0t, or with the plus 0 Vt, which corresponds to the ascent of the line segment upward. It doesn't really matter, but in order to stick true to the title that I declared for this episode, we'll keep it with the negative sign, and the equations of motion for the x component and the y component of the coordinate of the point B, they precisely represent the law of motion of the point B that we were asked to find in the first place. Squaring both sides of the last two relations, then adding them together, we have x squared plus y squared equals r squared 0, which means that at all times the point B is located on the outer surface of a right circular cylinder, and the axis of the cylinder will coincide precisely with the z-axis, and each and every generatrix of such a cylinder will be parallel to the z-axis. So if we were to portray it somehow like this right circular cylinder, these will be the boundaries of this cylinder. The upper surface will go like this somehow, the bottom surface will go like this, and each and every generatrix will run like so, vertically, strictly vertically parallel to the z-axis. This is one surface when it doesn't account for the variance over the z-coordinate. And if we bring it in, for example, from the last equation shown over here for the y component of the coordinate of the point B, we can exclude time using the top expression, and that expression then will be the following. Without time, it will be y equal to minus r0 times sine of omega 0 over v0 z. You see over here y, z, x is excluded, and what is this animal? Again, the minus sign or the plus sign is irrelevant. What we have over here is another cylindrical surface whose generatrices are parallel to the x-axis. And if you were to plot this type of surface, you will see that it is basically a wavy cylinder that looks a wavy cylindrical surface that looks like this, runs like this up and down the z-axis, and the generatrices actually will be parallel for this surface, will be parallel to the x-axis like so. And the only thing that this sign will affect is the orientation of the waves of this cylindrical surface, this way or that way. Of course, again, you should, when you visualize this cylindrical surface that runs like this, you should understand that it runs actually somehow like this, where the generatrices of this cylindrical surface are parallel to the x-axis. And again, this wavy cylinder does not enclose any finite volume. If we chop off our technically infinite right circular cylinder shown over here at the logical bottom, logical top, then such a surface will enclose a finite amount of volume. And this surface over here, the cylindrical wavy surface that fundamentally or structurally looks like this, if you were to plot it, it will look like this. it does not enclose any finite volume, but it should also be understood quite easily. You can see this by the way the paper bends, that if we were to chop this cylindrical surface, wavy cylindrical surface, with the plane x equals 0, what we will have? We'll have precisely the sine wave that runs over the z or y plane, in this plane right here. Z or y plane, it will be sine wave. Consequently, the intersection of these two cylindrical surfaces, the right circular cylinder, whose equation is captured over here, and the wavy cylinder captured over here, produces precisely the trajectory of the point B. That's what we were asked to find in the item number 3. And the trajectory of that point will be the so-called A cylindrical spiral. Spiral, also known as a helix. And if, again, if in our law of motion we put in the time t equals 0, then this will correspond to initial position of our point B that has the following coordinates: r over x component, 0 over y, 0 over z. So our point initially will be located somewhere over here. Okay, fine. Then the minus sign tells us that, strictly speaking, by the title that was declared for this episode, our point will wind its way logically downward in a downward spiral. But we understand that this sign is cosmetic. If we put a plus sign over here, then our point, since I have more room over here, will climb or wind its way over the generating right circular cylinder in such a way that, again, the intersection of this right circular cylinder in this wavy cylindrical surface will produce exactly the curve that is known as a cylindrical spiral or a helix. And there is an entire family of such curves, but it will look roughly, let's say, as follows. If we take it that our line segment rotates in a sense, then there will be plus sign over here. Again, it's purely cosmetic, so let's try to depict it. It will be a cylindrical spiral that runs like so, this way, and then this way, and then this way, and this way into this guy. But what is important to understand over here, the one little technical detail over here is the following. Observe that what we are dealing with for the coordinates x and y are the trigonometric functions of cosine and sine. The way it stands right now, they are 2 pi periodic, which means that when omega 0 t hits 2 pi, our values will again start repeating for x and y, and that will be called a period of 1 complete revolution if we ignore the translational motion. From here it follows that for this period we will have evidently 2 pi over omega 0, but during that time our point will either descend or climb the height, let's say, or the vertical displacement, let's call it h, which will be v0 times t, since the vertical translation is uniform and unfolds at the rate of v0 units of time per unit of time. And that will be what? 2 pi times v0 over omega 0. And this is a constant. So as a quantity, this vertical displacement of the point during one time unit of time t, shown defined over here, this will be the climb, and we can visualize it as follows. Let's say I take the green chalk. This quantity is called a pitch. It's called a pitch of the spiral, and we can envision it as a distance that is measured along any generatrix of this corresponding right circular cylinder that is trapped the amount of the length of the generatrix trapped between two immediately adjacent segments of this here cylindrical spiral. For example, let's say we take this point as our initial point. During the time defined over here, it will make one twirl and it will come back to this point right here. Let's say this is our generatrix. Right here, the point will find its way into this. So if we construct a straight line that is parallel to the, let's say here, positive branch of the x-axis like this, so then this distance right here will be precisely h. This distance right here is h, and because both types of motion whose superposition defines the overall motion of the point B is uniform, the vertical translation and the horizontal rotation, and the numbers v0 and omega 0 are constant. It means that the pitch of this particular spiral is constant. It does not vary over time. So intuitively speaking, every twirl that winds its way over the outer surface of the generating right circular cylinder is spaced from its immediate neighbors by the same amount at any point here, 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 and so on. In my, of course, artistic rendition over here, it doesn't look so, but the mathematics of this experiment tells us that this is precisely so. Once we manage to deduce the law of motion from the verbal description of that motion, the task of recovering the fundamental kinematic parameters of the point's motion amounts to differentiation. And for the converse task, if we were somehow given some information about the fundamental kinematic parameters of motion of a given point, then the recovery of the law of motion would correspond to the inverse operation of differentiation, which is integration, which is way more challenging than differentiation. Differentiation is straightforward and mechanical in this case. So for the x component of the velocity of the point B as a function of time, we simply differentiate once the x coordinate over time, and we obtain what? Minus omega 0 r 0 times sine of omega 0 t. Then for the y component of the velocity of the point B, we have the first derivative of the y coordinate. It will be omega 0 r 0 times the cosine. Here the trigonometric functions flip. And what do we have for the z component of the velocity of the point B? Well, this will be the first derivative of the z coordinate of that point over time. And this will be over here. Let's do this. I will write plus minus v0, and the explanation for the plus minus is already straightforward. The plus sign in this equation of motion corresponds to the logically upward motion of the point over the surface of the generating right circular cylinder, and the minus sign corresponds to the logically downward motion. But this is just a cosmetic nuisance. It does not really affect the structure of our solution. The structure remains one and the same and is captured over here. So depending on the direction of the motion, we take either the plus or the sign. Plus logically up, minus logically down. And once we have that information, what do we do next? Well, next we write down the expression for the velocity, for the complete velocity or magnitude of the velocity of the point B as it traverses the cylindrical spiral at hand. And that is quite straightforward. This is the square root of v squared x plus v squared y plus v squared z. And what do we have again? Look at the pleasant sum of squares. Here the negative sign evaporates. The sign of square of the sine square and cosine square fall into the positive unity. And what do we have? We have the following: v squared 0 plus omega squared 0 r squared 0. This is our magnitude of the velocity of the point B. And look at this. And this is precisely why I designated all our symbols that do not vary over time with the subscript of 0. So it's straightforward and right in our face. Constant quantity, constant quantity, constant quantity. And square sums and square roots become constant quantity. So now we know that the motion of the point B over a cylindrical spiral, in this case, unfolds with a velocity that is constant by magnitude. But now that we know the magnitude, we can compute the direction of the vector of the velocity of the point B at any time by using the so-called direction cosines. And here I will take just a second to memorize these, write down these expressions, or you can also deduce them at any time, but I will take a short second and erase this material, move it up a little bit, and then we will write down the expression for the direction cosines. I do not want to insult your intelligence and make you watch me write this mostly, for the most part, boring formulas for the direction cosines. They are well known. The direction cosine between the given vector and the unit vectors that go which way. Let's say we will put these guys this way. This red unit vector Ex, this unit vector right here Y, this unit vector right here for Z. Small font, but you see what is going on. And the definition of this direction cosine is the corresponding component over the entire magnitude of the vector, component over the vector, component over the vector. We simply take these numbers, slug them in, and voila. But the interesting part over here, once we write down the seemingly boring formulas, here where a little bit of interest comes in. Look at this. Constant quantity, constant quantity, constant quantity. Oops. Variable quantity, t over time. This is a constant over here. Likewise, for the direction cosine with respect to the y unit vector over the y-axis, we have constant, 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 varying quantity, t. So the direction of the unit vector, let's see where can we put this point? Let's say we take this point right here. Our point B at some point turned out to be right here. The corresponding angles that the velocity vector makes with the x and y axis changes at all times. But look at the direction cosine that defines the direction of the velocity vector of the point B with respect to the z-axis. It is, again, I put the plus minus sign so that I keep true to my word, to the declared title of this episode, so you understand, for the descent, for the genuine descent, minus for the ascent, plus, again, structurally does not change anything, but what we have here is a constant quantity and constant quantity all over the place. And look at this. This is a constant quantity. That means that the angle between the velocity vector and the z-axis, or technically, let's say, if we do here the following through, remember that the point B at any point is located on a generatrix of the corresponding or generating right circular cylinder. So at this point, the velocity vector, let's use the, let's say, the green color over here. This will be the velocity vector, V. And that means that this expression over here that shows us that the direction between the, or the angle between the velocity vector and the z-axis remains constant, does not vary, it means that our point B intersects each and every generatrix of the parent right circular cylinder at the constant angle, one and the same angle. This is the interesting bit, and once you understand what is going on, we can imagine or envision the entire family of like spirals. For example, in the near future, we will deduce the equation for the spiral that unwinds with respect to, let's say, this will be the, again, z-axis, y-axis, x-axis, but this will be a what? A right circular cone. So the spiral that unwinds over this guy will have an interesting property, because here a generatrix will run from the origin this way, that way, and that way, and here you will have to see, will the motion of a point over a specific spiral or a conical spiral will have the same property, yes or no? Think on your own, maybe try to solve this problem on your own. This is how you get involved with mathematics and physics, and also in the near future we will solve a problem that gives birth to the so-called curve called loxodrome. There, with the loxodrome, the idea is the same, except that the motion of a point unfolds not over a cylinder, right circular cylinder, or a right circular cone. It unfolds over a sphere, and over the sphere we have these things called meridians, like this. These will be our parallels right around this way, but we will see that a loxodrome is a curve on a surface of a sphere, where again the velocity of the point that moves over that surface forms the same angle with each and every meridian, like this. Tangent, velocity vector, and the angle between them is the same. So in other words, as the point traverses the globe, if you will, it intersects every meridian under the same angle, and we will deduce an equation. But the property of this such a motion over a loxodrome is the same as the property that we witness over here. The point that moves over a cylindrical spiral that sits over a generating right circular cylinder, motion, the vertical translation motion is uniform, the horizontal rotational motion is uniform. As we can see, as we just proved, as a tiny theorem, if you will, that such a point intersects each and every generatrix of the parent right circular cylinder under the same angle, which means that this angle with respect to the z-axis is the same and does not vary over time. Here again, I do not want to insult your intelligence and watch me write down the derivatives of the coordinates of the components of the velocity in order to compute the components of the acceleration of the point B as it winds its way over a cylindrical spiral here. The only difference with respect to the previous segment is that we crank up the order of the derivatives by 1. So second derivative over the coordinates for the acceleration, or the first derivative over the velocities. Trivial task, not interesting. This is where it really begins to get boring. We now know the acceleration over the z-axis or along the z-axis is what? It vanishes. It is 0 because the velocity is constant, the vertical velocity measured along the z-axis. Square, 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 plus, 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 square root. This gives us the magnitude of the acceleration of the point B, and this magnitude comes out to be what? Cosine square, sine square, everything nicely, the minus signs evaporate, square root of the whole thing comes out to be this, constant quantity, boom, voila. The acceleration by magnitude, it is important to understand, by magnitude, remains constant over time. You also tell your examiner that the direction cosines of the acceleration vector are wrote down the same way: component over the length of the vector, component over the length, component over the length. Write down, write down, write down. Why is that? Look at this. Omega squared r0 and omega r squared, omega squared 0 r0 cancel out, and we have negative cosine, negative sine. You have this, and at this point you tell examiner happily that this fact means that over the set of real numbers, the very first real number when the cosine flips to 0 is what? Pi over 2 radians, 90 degrees. What does that mean? That means that the complete or the total acceleration vector of the point B is what is orthogonal to the z-axis. So if we take our point B, take a snapshot of the point B as it winds its way over the cylindrical spiral, ka-ching, and then we cut this cylinder through that point with the plane that is perpendicular to the z-axis somehow, then in that plane they will point somewhere the vector, the complete vector A. It will be in that plane perpendicular. At that point, the examiner will look at you and say, okay, hot pants, what can you tell me about the actual direction? Where does the acceleration vector point to actually? Somewhere in the plane perpendicular to the z-axis or to the axis of the generating right circular cylinder is fine, but it's not good enough. You can't do better, do better. So here just about the only place where some intellectual voltage comes in. Yes, you confidently computed the cosine, the direction cosines. You showed the examiner that you know the material, everything is wonderful, but here is the maneuver that you're expected to execute. Let's concentrate on this, cosine and sine. What are these guys? The sine and cosine. This is the observation that you're expected to do in real time in a verbal face-to-face real-time examination. So here you write it down as minus x over r0, you see, minus y over r0. You see, this is the observation that you're supposed to make. And what are these guys? What is this quantity? This quantity and this quantity. Well, this is, if you will, the direction cosine. This is cosine of alpha, let's say, and this will be the cosine of beta, let's say. And I will use, okay, let's say yellow chalk. You see, if we project the point where we captured it at the moment onto the x or y plane, this will be the angle alpha. See, this way. And this will be the angle beta. This will be the angle beta, and this is our point right here. See, so these quantities correspond to the direction cosines, not of the acceleration, but of the coordinate of the radius vector of our point within the x, o, y plane. That is the bit that you're expected to understand, grasp, comprehend, not just juggle formulas mindlessly, computing derivatives. A robot can compute the derivatives, but now we need to bring in our human ingenuity and creativity, in some sense, if you will, and inhale into this robotic and mechanical boredom some intellectual sparkle, something interesting. And this is the observation you're supposed to make. And what does that mean? That means that the direction cosines of for the acceleration vector and the direction cosines for the radius vector for the position of our point B differ only by what? They only differ by the sign, but not by the magnitude. Only by the sign, but not by the magnitude. What does that mean? The next conclusion that you're supposed to make and tell your examiner is that that means that not only the complete or the total acceleration vector lies in the plane that is orthogonal to the axis of the generating right circular cylinder, but it always points precisely at that axis. In other words, let's say if we cut our plane with our cylinder with the plane like this, it will come through this point. So here is where the acceleration vector A will point precisely at the axis of the generating right circular cylinder. This is the information that you're supposed to be able to extract from this boring and mechanical manipulation. And once you are done with that, you are getting close to a passing mark for your problem. You will pass that problem. And the final thing is the curvature of this trajectory at any point as the point B runs along the trajectory. And here we observe the following. Recall that when we computed the magnitude of the velocity, the total velocity is a constant quantity. That means that the tangential acceleration by magnitude is equal, let's say if you prefer these guys to use the magnitude signs, is the first derivative of the tangential velocity over time, which is the velocity of the point. But the velocity is constant, so the tangential acceleration of the point in this case is what? Is big, fat, 0. And that means that the total acceleration by magnitude that we computed over here is precisely the normal acceleration of this point, which is omega squared 0 times r0. You see, so here, even though our, let's write down over here, I will write it down maybe in, say this way. Remember our expression for the velocity, it was v squared 0 plus omega squared 0 r squared 0. That was our expression for the velocity. It's constant. So even though the motion of the point B over a cylindrical spiral is uniform in the sense that the magnitude of its velocity remains constant at all time and does not vary over time, its total acceleration is still not 0. It is distinct from 0. Look at this. Distinct from 0. These are non-zero real numbers. And why is that? What's the explanation? Well, the explanation is straightforward. Even though the magnitude of the vector of the velocity of the point B remains constant, its direction is changing all the time. Its direction is changing all the time. And even though the tangential acceleration is 0, which precisely reflects the fact that the magnitude of the velocity remains constant, its normal acceleration is not 0, and this gives us the hint for the computation of the curvature of the trajectory of the point B. Remember from your middle school physics days when you were studying the motion of a point over a circle, you were told that the magnitude of the normal acceleration of such a point is what? V squared over r, where r is the radius of the circle over which the given point runs. But we are not in Kansas anymore. No offense to all my friends from Kansas. We are playing in the big league, and in the big league, the point can move over a trajectory that has not a constant curvature, but a curvature that varies at every point. So here, this is cutting the long story short. We have it that for the magnitude of the normal acceleration, we have v squared over rho, where rho exactly is the curvature. There are many ways to define the curvature here. We take it in the kinematic sense. There are many wonderful formulas. Some of them are quite horrible. Remember, the curvature can be given in the coordinates, for example, x and y. We can give the curvature in polar coordinates and all sorts of wonderful other material. But here we already know the magnitude of the normal acceleration. Remember, we computed it based on the fact that the tangential acceleration that keeps track of the change of the magnitude of the velocity is 0. This velocity is constant. And the normal acceleration keeps track of the change of what parameter of the velocity? direction. That's right. So here we have it that rho is equal to v squared divided by the normal acceleration, and that is v0 squared plus omega squared 0 r squared 0 divided by omega squared 0 r 0. So now we are feeling quite generous. We share the denominator with all the summands in the numerator, divide this by the denominator and this by the denominator, and what do we have? Look at this. Omega squared 0 cancels each other out. One copy of R0, one copy of R0, one copy of R0 survives over here. As such, we can write it that as a function of time, the curvature of our cylindrical spiral is given by the following expression. R0 plus v squared 0 over omega squared 0 r0. This is the result that the examiner was expecting you to produce. And what other observation you make? Constant quantity, constant, 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 constant. Everything is a constant. So the curvature is also a wonderfully constant quantity in this case. The curvature of such a right circular cylindrical spiral, if you will, is constant. And from your middle school days, you remember what kind of curves have constant curvature. Well, you know, straight line. A straight line has constant curvature. You know that a circle has a constant curvature. And now you, to your baggage of curves of constant curvature, you can add this one, the curve that is generated by a right circular cylinder, and with a romantic story that I invented for you about the descent of a rotating line segment. And here, before we complete the solution of the physics problem, I would make a note that if you are conducting or putting together math circles or physics circles, remember that very quickly, in an expedient manner, we deduce the law of motion in this case, which was given by three equations of motion in z of t equal. So here, the description of this motion was invented by me, let's say, but this is not that difficult to invent. Just about anyone will do that. And this is the point. Instead of giving a verbal description of this motion and asking your students to deduce the law of motion, you can do the converse problem. Give the equations of motion like this, in this form. R0 sine omega 0 t, and then R0 cosine omega 0 t. And then ask your students to invent their story that will give a verbal description for a known bunch of formulas. Our next challenge will be the challenge in computer science. It will be marked as Season 3 Computer Science Problem number 6, shown in the upper left corner on your screen. And this challenge will consist of two parts. First, in your own words, you are to explain the inner mechanics of the Narayana's next linear permutation algorithm. Do the best you can, and also mention its characteristic feature. For example, what is the difference between the Narayana's version of the next linear permutation algorithm and the Johnson-Trotter linear permutation algorithm? That's the test number 1. The test number 2, you are to implement your explanation, if you will, of how the Narayana's next linear permutation algorithm works, preferably in the best programming language of all times, C. Meanwhile, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my explanation of the inner mechanics of the Narayana's next linear permutation algorithm and its implementation in the best programming language of all time, C.